So I chose to use cytochrome oxidase subunit 1 or the Koi mitochondrial gene to create a phylogenetic tree that you can view and manipulate using the confines of Galaxy, and you'll also see uh, external platforms. So just a little bit of a background. Phylogenetic trees are hypothesis of evolution. You can take multiple samples and input rather nucleotide information, protein information, morphological information, and it'll use either distance-based or maximum likelihood-based methods to calculate and give you a model as to what we predict the evolutionary pathway was. Like I said, it is only a hypothesis and it gives us a rough idea. It's not definitive, and realistically, there isn't uh gonna ever be a 100% foolproof method, but for my method, I chose to go down the route of maximum likelihood, which uses probability to give you the most likely pathway that brought you to your current data points. If you look at the diagram, you'll see different nodes, which is where two lines intersect, and that represents a common ancestor. And from those nodes, where they branch off, that shows diversification and the creation of new species. So, yeah. A little bit beyond my data set and methods, I chose to use fauna or animals such as humans, chimpanzees, wolf, domestic cat, cattle, horse, chicken, and an African clawed frog. I wanted a diverse enough set of species that you could easily detect and understand what is going on, and we can ultimately predict with confidence whether or not our model is reflective of um, concurring data. And the pipeline that I chose through Galaxy was to take my FASTA files from NCBI, upload them, align them using MAFFT, and then use the FastTree tool to create a maximum likelihood of the data. This is on the right, essentially the exact pathway that I took. I try to keep it as simple as possible for the screenshot, but we have the eight species FASTA upload, which is just a file including all of the species that I used in my data. And then from there, I use MAFFT on that data. And from there, I took the aligned data and uploaded it to the fast tree tool, which it then produced a fast tree that you can use Newick display on to display, and you can see here. This isn't the correct or most accurate form of display, as you'll see later on that there was anomalies and issues with the limits of Galaxy. So a little bit behind Galaxy, I chose it because it was accessible and moderately powerful. It gave us enough of capability and accessibility, but it was limited and it didn't allow for rerouting, which is necessary to give your tree almost a reference to know where everything should go in context to one another. Without that rerouting step, your data is essentially misconstrued. So after I rerouted the data using ITOL, which is Interactive Tree of Life, an external platform, I was able to produce this, which is accurate and reflective of concurrent data. There was a slight anomaly in the fact that chicken and wolf were extremely grouped up, but that's likely an artifact of a longer series of deviations or diversifications that I simply couldn't account for due to the limited size of my data. But it also serves as a reminder for the ethics and necessity of good research, where you simply cannot look at one thing or run a test one time and be okay with the results. You have to use it in context and keep on going at it until you can confidently say that this is a good indication of what truly occurred. So, in short, it worked and it was easy to follow. That was my entire goal, as I think bioinformatics struggles with the universal aspect and the collaboration. And this method, although it seems simple and limited in its applications, you use the same process to apply to things such as disease tracking and species identification. Showing the capabilities of bioinformatics is simply what we choose it to be. So thank you for